Friends, welcome to the 15th lecture on Advanced Steel Design course. In this lecture, we are going to talk about the dynamic material strength and the response criteria with respect to steel as a construction material. Okay. We already said that the design of structures is to aim creating resistance against the loads. In fact, to be very clear, if the load effects arise out of accidents like fire, explosion, impact, etc., then the material strength need to be explored under such conditions. Because the material strength varies under such impulse loading or under such time variant dynamic loading. For example, structures under blast loads undergo plastic deformation, because this is required to absorb the explosion energy. Okay. Therefore, these type of loads also inherently affect the dynamic characteristics and strength of the material. Okay. On the other hand, structures under conventional loads like dead load, live load, etc., shall remain or continue to remain in elastic range. So, the design philosophy also intricately address the type of load and the preferred response. The type of load and the preferred response. So, now the design procedure itself is multidimensional. The design objective itself is varying. Therefore, we cannot have a single design procedure which can address all kinds of loads and all kinds of materials. Okay? Let us be very clear about this. I hope you are getting the point what I am trying to say. Okay. Having said this, let us quickly understand what is the difference between static and dynamic response, because it is very important for us to learn this very briefly so that we know how the dynamic material strength is understood. Okay. Now, let us for example talk about conventional loads. Conventional loads such as live load, dead load, in fact I would also call wind load as a conventional load. They are generally applied relatively at a lower speed or lower rate of application on the structure. relatively they are lesser speed of application, and usually they remain constant for a long period of the structure. Okay. Now, when I say I have to compare the lower rate, longer period, then this is generally in comparison to the time period of the vibrating system. So, compared to the time period of the vibrating system, these are all lower rate of application, longer period of stay, etc. Okay. On the other hand, if you look at blast loads, they are applied or act very rapidly, and they will give rise to the stresses on the member very rapidly. So, one can very well say blast load looks like a transient phenomena. So, what does it mean? The structure will or expected to return to normal operational conditions in a short period of time. So, time period plays a role in understanding the effect of these loads on the structural systems. Okay. Therefore, in relationship to this, what will happen in the conventional design? In the conventional design, stresses are limited within the elastic range, whereas in blast resistant design, for example, yielding should be permitted, because it is one of the form of absorbing the explosion energy. Okay. So, since yielding is allowed, member response is moved to plastic region. So, during this process, it continues to absorb the blast loading or blast energy by balancing the kinetic energy of explosion against the strain energy of the member. Now, when we accept this statement, we say that now the total strain energy is a function of 1. Dynamic material properties, and 2. section properties, and 3 the amount of plastic deformation permit. So, the total amount of blast energy required to be absorbed, let us say we would look into the demand, right. So, the demand is from the blast energy. So, the total amount of blast energy need to be absorbed should be a function of the peak load and of course, as you correctly guessed, duration of the blast small t and peak load, let us say amplitude A bar. So, now the adequacy of the blast resistant design of structural systems is based on the maximum deformation rather than the stress level. Okay, that is very important. Let me write down here. So, now the blast resistant design philosophy should be based on the maximum deformation level. It is not based on the stress level. So, therefore, a conventional design which talks about the stress as an indicator in the design parameter is of no use under these kinds of loads. Okay. Having said this, let us see how the material responds. We have seen how the structure responds. Now, let us see how the material responds to this. When a material is loaded rapidly, it cannot deform at the same rate at which the load is applied. So, what I mean to say is the rate of loading cannot be equal to rate of response or rate of deformation of the material. I am talking about the material, not the structure now. Okay, I am talking about the material response. So, this disagreement creates an increase in the stress level at which yield occurs in the material. It also affects the ultimate stress achieved in the material. Okay, these are the two influences caused by this disagreement. Okay. So, what will be the immediate consequence of this? The immediate consequence will be ultimate stress will be reached before rupture. That is the problem. Okay, that is a very interesting understanding which we must know about the material behavior when this or such disagreement is seen. Having said this, we now clearly say increase in strain rate leads to strength increase, it leads further to a consequence that member develops structural resistance in excess of the static loads. So, this strength increase is quite significant. But its effect on the design is not too important, because the rate of loading remains only for a very brief period compared to the service life of the structure. Therefore, this benefit of increase in strength cannot be accounted in the design as a significant parameter. Okay. Having said this, when we compute the fluctual response, of the member, we generally do not account for the strength increase caused by the increase in strain rate. This statement is kept in mind and applied to steel as a material. Please note that this in the background information is we are talking about steel as a construction material. Now, if the strength is ignored, as we said in the previous sentence, then the forces or the loads at the joints or connections will be underestimated. Please understand why. Friends, please note, this is an internal effect caused by the member. So, I should say this is a reaction. Now, this reaction will have a counter effect on the joints. So, whatever loads coming on the joints now, whether it is external by the moment caused by the loads or internally caused by the material or the member behavior, you will be underestimating that. Okay, there is the danger here. Okay, there is a danger here. You are underestimating that. Now, you ask me a question, how this is accounted then? In the design, because this has to be accounted in the design. Na? How? This is accounted in the design by using a factor called dynamic increase factor, DIF. This is very much prevalent in blast resistant design or design under accidental loads. Let us go at one step ahead and discuss about the resistance deflection function. Generally, friends, in flexural response, stress rises proportional to strain in a member. Okay, that is a usual practice. Generally, it rises like that. Since resistance offered by the material primarily and by the member, because form dominance is also a function of stress, it rises in proportion to strain, is it not? So, after the material extreme fibers of the cross section reaches the yield point or the yield strain, relationship between stress and strain becomes non-linear. Please note very carefully here, this becomes non-linear only at that instance when the extreme fiber alone reaches yield strain, not the full cross section. Please note that. Not the full cross section, only just when the extreme fiber reaches the yield strain, stress strain behavior becomes non-linear, okay, immediately. There is no proportionality between the rate of increase of strain and the rate of increase of stress. They are no more linear, right? I am talking about steel as a material in mind. Having said this, further, as the extreme fiber yields, stress in the interior section also begins to yield because the load will be transformed, the strain will be transformed to the next adjacent fiber, right. So, that starts yielding now, and this will initiate a plastic hinge. We will talk about the plastic hinge and plastic design in detail in the next module lectures, but let us say it initiates a plastic hinge. Plastic hinge is an imaginary section that yields and therefore rotates without any additional moment. That is, at plastic hinge, the moment capacity which makes the hinge to rotate is m suffix p. but any moment addition to this is not required. You keep on rotating at that moment. Okay. So, plastic hinge will be initiated. So, where they will initiate? As you correctly guessed, these plastic hinges will initiate at the sections of maximum bending moment. I am talking about flexural failure. Maximum bending moment. Okay. If premature buckling is prevented, we will talk about the buckling failure in detail, but let us know a hint here. How do you prevent a premature buckling? Ensure that the section has desired compactness limit. Compactness limit is a factor given in the code which depends on the cross sectional dimensions of the member, and if that factor is satisfied, the member or the sizing of the member will not initiate premature buckling. Okay. So, it is simply a geometric choice of a cross section, right. For example, B by D, H by T, B by TW, H by TF, etc. right. So, if this is satisfied, then premature buckling will not happen. Let us say if premature buckling is prevented, then the deformation of the critical or deformation at the critical section on the member can be related to the strain producing a relationship between resistance and deflection. Let us try to plot this. In the x axis, let me plot the deformation. In the y axis, let me plot the resistance. And let the curve has 3 slopes, let us say. Okay. Let us see different distinct points. We call this as y maximum, this is y yield point, and this is y elastic. Okay. We call the corresponding values as Ry and Ru. Okay, Ry and Ru. So, area under this curve, as we all know, with respect to x axis, will give me the strain energy. Okay. Having said this, let us say an elastic resistance is the level at which the material reaches yield at the critical location or critical section of the member where the moment is maximum. Okay. So, this is termed at the first yield. Now, beyond the first yield point, plastic regions will be formed. In the section, and it will lead to elastic plastic deformation, correct. In this condition, at this condition, internal resistance continues to decrease because plastic hinges have formed, first yield has occurred. Internal resistance continue to increase as the stress in other locations or other sections rise in response. Okay. So, response now will shift to the adjacent next critical sections, and the response keeps on rising in adjacent sections. Okay. But this will occur at a lesser slope than the elastic region. Please see the curve. Please see the curve. The slope of this, if it is theta 1, if this is theta 2 will be far lesser than theta 1. Okay. It will occur. It means a large deformation which is plastic will occur at a small rise in strength gain. Okay. See here, a large deformation will occur for a small rise in strength, right. So, up to this place, this is proportional. Beyond this, it is not. Okay, that is what we are emphasizing here. Okay. So, during this period, some sections of the member are already in plastic region, while remaining are in elastic region, correct. And this variation will happen along the member, not across the cross section. Please understand, this will not happen across the cross section. Can you tell me why? Very simple. The moment varies along the span. Okay. The response is directly related to the moment demand. So, this variation will happen along the member, and there will be a continuous shift of critical sections from A, B, C and so on, which will slowly get plasticized, while the remaining will become elastic. Okay. So, friends, in this lecture we are learning about the dynamic strength variation and elastic plastic response behavior under blast resistant design procedure. Not necessarily blast, I can even call this as accidental loads. Okay. So, hope you will be enjoying this and you will be following these lectures back to know more about this. Please have a look at my advanced steel design book, which is a very useful handout and gives more information about these processes for your comfortable pace of learning. Thank you very much. Have a good day.